Okay, thanks Robin. So changing a little bit, we're going to engineering now, so we have to keep things simpler so we can do things. I'm going to talk to you a little bit about offshore structures in large ocean storms. So the first thing I want to do is just define what I mean by large storms. So I'm going to show you a video, and then I'm going to talk to you about the type of structures that we have to design to withstand or to stay functioning after large storms. So this is a sound. This is a video from YouTube, so nothing that I took personally. But you can see this is a vessel that's moving in the direction of the waves are approaching, and some very large waves. This particular wave we just get over. You can see there's a second large wave approaching now. This is your worst nightmare, I guess, if you're on a vessel. That wave breaks and then hits the vessel. So just gives you an insight. These are huge storms. On the northwest shelf of Australia, we think the largest waves can get up to 30 metres or so in height. So really large, driven by cyclones on the northwest shelf. So large storms are large and dangerous, and I guess our job is to think about how we can design for them. So that was a vessel that was moving in the ocean. These are sort of a cartoon of the different things that we consider in our research, and by we I mean myself and a collection of other engineers within the Oceans Institute at UWA. We do all sorts of things. On the left-hand side of this cartoon is some applications in offshore oil and gas. So on the surface we worry about, on the very top left, we worry about green water, which is where water can wash up onto the top of a vessel, just like that video. And we worry about how much water may do that and how much force the water may impart on the structures on top of the vessel when that happens. Just to the right of that is another example, just a cartoon of the big massive Prelude FLNG, which Shell are currently in the process of bringing to Western Australia. This is the largest ever offshore structure that will be permanently moored on the northwest shelf of Australia. It's about 500 metres long, and it's basically a giant refrigerator where they take natural gas out of the seabed, process it, and then ships will come alongside and offload. These structures, this floating structure will always be there. It will have to survive cyclones like the waves you just saw in the video. They're the things at the surface in oil and gas, but there's also a lot of stuff on the seabed. So the bottom left shows some examples of subsea infrastructure and pipelines which run on the seabed. These pipelines carry oil and gas back to shore. And these are also susceptible to large storms because although there's big waves on the surface, those big waves cause currents all through the water column, and we have to worry about whether these pipelines are stable or not in large cyclones. And on the northwest shelf of Australia in particular, I don't know if I've got my mouse here, these pipelines are often filled with natural gas, so they're quite light, so it's hard to keep them stable. So we worry a lot about those and how they will perform in large storms. Towards the middle of the picture is some renewable energy, and the big device in the middle there is a cartoon sketch of the Carnegie, now it's called Carnegie Clean Energy, it used to be Carnegie Wave Energy, their device, and we work with them to understand the performance of their device in large storms, and I'll show you some more detail on this in a minute. We also do work with some local innovators, in particular a company called Subcon. They're designing artificial reefs to enhance fish life. And again, the issue there is whether these artificial reefs will remain stable in storms. We don't want them to wash up on the coastline. And we also do some stuff in the river. So putting model structures in the Swan River and trying to use the naturally occurring wind waves a bit like a large wave basin. So we can deploy, for example, model scale vessels and look at how they move in the river and try and understand something about the motion of them so that we can understand how full-scale vessels might respond in very large waves. So that's a range of things. I'm going to focus on two today. Of course, you can ask me questions about all of them, but these are the two I'm going to focus on. One is the Carnegie CETO device, so this one here. And this is work not just done by me, but by myself and colleagues. So Jana and Hugh are not here, but they've worked on this a lot with me, and also Ashkan Rafi from Carnegie has worked on this. And I'm also going to talk about pipelines, because pipelines have been a big part of UWA's research over the last 5 to 10 years. And this is work that I've done not by myself again, but with Liang, Hongwei and David White in particular. So if we start with the Carnegie device, it's very hard for us to do numerical modelling of these structures because these structures are in very large waves and they're moving a lot, and so it's very difficult for us to model that numerically or theoretically. So often what we need to do to understand how these structures respond in large storms is to do what we call model scale experiments. And this is an example here of the Carnegie device. You can just see it, this yellow in the water here. This device is about 1 metre in diameter, and it's representing what we think a full-scale device would be, which is 20 metres. So this is what we would call a 1 to 20 scale model. And what we do is we have a wave basin. This is a wave basin in the UK, at Plymouth, in the UK. And we produce waves, and these waves are irregular waves. We produce them to try and mimic ocean storms. And so the waves have also been scaled back, so their size, their height in particular, is 1/20th of what we expect it to be in real life. And what we do is we do very long simulations in labs where we produce these waves, and the waves are random, so we think of them in terms of statistical, frameworks. And if we wait long enough, we should see a very large wave, and if we don't wait for very long, the chances of getting a large wave are smaller. And what we're interested in is running these experiments for a long time to see what the largest motions of this wave energy device are. And by large motions, what do I mean? Well, this wave energy device is effectively a buoyant buoy that will move backwards and forwards in the waves, and it's connected to an extendable cord. This extendable cord extends, that's what I mean by extendable cord, and you can imagine that the loads on the foundation here are related to how much extension I have in this line. So imagine that's an elastic band. If I stretch it, the force on either side of the band is getting larger. So what we're worried about with these wave energy devices is they'll move a lot in storms, they'll extend and contract a lot, and when they extend in particular, we'll put large forces on the foundations, and we may rip the foundation out of the ground, and the device would then be free to move, and that would be a disaster. So the wave energy device would wash up on the shoreline. So a lot of these experiments are about us understanding in random waves, characteristic of real oceans, what are the extensions in this line. And in an experiment, the way we try and replicate that extension is sort of shown in this little picture I just popped up on the middle bottom right. You can see here there's a pulley at the bottom, and we've got a line here. That line goes up to a torque-controlled actuator, if you like. So we can control essentially the springiness of this line, and as this device moves around, this line will extend and contract. So what we do is we take very long measurements, as I said before, and we just want to look at the extreme motions, okay? So I've got a plot here. This is going to look a bit complicated, but there's a plot on the horizontal axis. We've got time, standard time that's been normalised so that at 0 time we've found a situation where we've got maximum extension, okay? And on the vertical axis we've got the extension here in metres at model scale. So what's happened is we've got lots and lots of responses or extensions throughout a particular experiment, and if we just focus in on the 20 largest motions, which are sort of shown here by the different coloured lines, we start to get a feel for what the device is doing when it's extending the most, okay? And then what we do is we then have a look at what individual waves are causing this extension. And this is where it gets a bit complicated. So I've got a figure now, again, of time, same axes. And on the vertical axis, we've got the water surface elevation. So this is a wave in time. And we get a feel for what type of waves are giving us the largest extensions. And what we tend to find, which is really quite convenient, is that very similar looking waves. So all of these different coloured lines are similar shape. They're all representing a type of what we call wave group in the ocean, and all of those particular types of wave groups are leading to this particular type of response. Why is that useful? Because it means we don't necessarily have to run long random simulations anymore. Once we know what type of wave group gives us our largest response, we don't have to wait for it to occur. We can just produce it directly in an experiment, and it allows us to fast forward, if you like, to the extreme event in a storm. And so what we did in Plymouth is we understood what particular wave gave us the largest response, and then we just did an experiment, and here's a snapshot of the experiment. where we have one wave only. And this is the wave approaching from the left here. Here's the wave energy device. That wave approaches, it causes the device to move. It has a very large extension event which matches the maximum extension event we'd expect in a storm. And we're able to study in about a minute exactly what this device would do in the extreme condition. We can also, because we've now dropped the whole time down to a very short simulation, we can try and model this numerically. So here's a plot from Ashkan's CFD simulation where we're doing numerical modeling to try and reproduce what we see in the experiment. You can see here that the top picture corresponds with this, and the device is just popping through the surface, and then this picture corresponds with when the crest of the wave comes through. So this is in a nutshell us trying to understand the response of a wave energy device and using some interesting statistics to describe what the extreme response is and what wave group causes it. So that's my first example. My second example is to do with pipelines, and here's a picture of a pipeline on the northwest shelf of Australia. This particular pipeline is laid on a sandy seabed, and this one's in about 120, 130 metres of water. Now at this water depth, the currents that the pipelines see could potentially move the pipe, so we're a bit worried about that. But of course the sand grains next to the pipe are smaller, and we know that they'll be easier to move. So one thing we have to take into account is, before getting too hung up about the stability of the pipe, we need to think about what will happen to the seabed around the pipe as it experiences different currents. Why is that important? Well, here's a sort of a digital sort of picture of a pipeline laid on the seabed. This is about 2 months after it was first laid or put onto the seabed, and you can see the pipeline sitting relatively proud of the bed, so it's susceptible to big, I guess, hydrodynamic loads. If we come back to this pipeline a few months later, or in fact a couple of years later, we can see that it's changed dramatically. And what's happened is all of the sediment around the pipeline has moved, because it's easy to move that sediment, and the pipeline's experienced what we call scour. The scour has gone under the pipe, and the pipe as a result is lowered down into the seabed. This is the process of self-burial. It's a fascinating thing, and it's very useful in pipeline design, because once this has happened, the pipe is much more stable. It's sheltered from large hydrodynamic loads because it's lowered into the seabed, and it's also got larger what we call lateral soil resistance, because there's more soil in contact with it, so it's harder for us to move it sideways. So this is a really interesting phenomena that occurs for pipelines on sandy seabeds. This example is from the Northwest Shelf, so it happens here in Western Australia. And the key for us is, can we understand if this occurs for a particular pipeline that we're about to design? And if so, can we factor this into our design approach? If we can't, we have to make the pipeline stable in other ways, and that could include putting thick concrete coating on it. It could include putting concrete mattresses on top of the pipe. All these things are what we call stabilisation measures, and they cost a lot of money, up to $1 million or so per kilometre. So if we can say that this self-burial will happen, we could save a lot of money, obviously. Okay, so to give you an idea about how a designer might try and bank this sediment transport, or this scour effect, it's interesting to think about the life of a pipeline during a storm. Now we know storms don't just appear out of nowhere, they're a gradual increase in severity over time. They reach a peak of the storm and then they decay away. So this is a plot here of Tropical Cyclone Olivia, and you can see how it's, over a period of 36 hours or so, the significant wave height, or I guess the average wave height, has increased to about 12 or 13 metres, and then it reduces again. We could think about whether the increase in the wave height here, we know that as these wave heights are increasing, we could be moving sediment, so we could be causing this scour to occur. And what we want to know is, at the peak of the storm, how much scour may have occurred, and would our pipeline be more stable than what it was when it was first laid? So a couple of simple experiments we can do using, again, model scale facilities. We could think about a hypothetical storm that doesn't have this ramp up, and so the HS, or the average wave height, just automatically jumps up. And if we were to do an experiment of this in our flume, and this is the O-tube flume at UWA, we have a pipeline here, and we've just subjected it to very large waves all of a sudden. And what happens is there is no time for any sediment transport to happen, so we've got sand here, but there's no time for any scour because the waves have just increased really quickly. And those waves have increased to a point where they can make the pipeline move and becomes unstable, and that's dangerous. Instead, if we model something that's a bit more realistic, where the wave heights are increasing gradually in time, what happens is a very different story. The pipe starts from the same condition, but then we start to get this scouring phenomenon happen. And you can see here we've got a tunnel that's opened up underneath the pipeline. We're looking at the side here of a flume. So if I cut a section through the flume, it looks a bit like this. We're seeing this scour hole at the edge here, and the pipeline is experiencing scour from both sides, and it's got a bit of sediment in the middle. And as the scour progresses towards the middle here, the pipe will begin to sink into the seabed. And so if we see a bit later on during the development of this storm, the pipe is now sunk down quite low, and then at the peak of the storm, our pipe is almost buried. So this pipeline in the second example can withstand a much larger storm than the pipeline in the first example where the waves increased all of a sudden. So this is hopefully giving you a bit of insight into how complicated maybe pipelines can be, but how there are big advantages from clever engineering for offshore developers. And that's it. Okay.